Another kind of energy from the sea, which is similar to the tidal energy, is the energy from waves. Waves energy. It is true that near the seashore you also have huge waves. So first of all, you need to have huge waves. Small waves that you see near the sea are not particularly useful. They will not have enough energy to be converted into useful amount of electrical energy. So the waves have to be huge. One thing. And secondly, they have to be even the strength of the waves has to be strong. So they have to be the strong waves. And obviously, as before, it has to be near the sea. The location has to be near the sea. So call it advantages. Advantages would be same as the tidal. And the disadvantages will be that they have to be huge and strong waves, and again near the sea. So what we play the same game. What we do is we utilize the kinetic energy of the strong big waves. We convert into pass that energy onto the shaft of a dynamo, and this energy converts into electrical energy. Now note one thing. What was the source of the tidal energy? It was the gravitational pull of moon. What is the source of the waves energy? Why are the waves formed? They are formed because of strong winds. So they are formed by strong winds. And who's responsible for the winds? The sun. What I'm trying to tell you is that even though we call it energy from the sea, ultimately the agent to provide this energy is the sun. As we will see, we are going to summarize the role of sun in this energy scenario. So energy from the sea is basically from the sun in this case. Then there is something else called ocean thermal energy. The word thermal means something that has to do with heat. Now where does this heat come from? As you know, water has a high specific heat capacity. Water has high specific heat capacity. So what happens is that on the sea surface, because of the sun rays, again the sun plays a very vital role. The top surface is hot. It doesn't lose, because it has a high specific heat, it does not lose its energy, heat energy very fast. So it remains hot. Now water is a bad conductor of heat, and the convection currents are not in the downward direction, and therefore you will have the lower levels of water cool or colder. So there is a temperature gradient. We call it a temperature gradient. That means there is a change in temperature from top to bottom. There is a decrease from top to bottom. And the temperature difference can be utilized. So what we do is, the depth has to be roughly 2 kilometers. If it is 2 kilometers, the difference is roughly 20 degrees centigrade, which is good enough. Only if the temperature difference is of this order 20 degrees centigrade, then only this kind of energy is feasible, right? Again, as you would realize that this is not so easily possible. What happens is the process in which we can convert this energy is like this. The hot water is used to boil. You would notice that its temperature is not going to be 100 degrees centigrade, so it cannot be boiling water. It doesn't have that high temperature, the top surface. It boils something which has a low boiling point, right? So it is something like, say, you would say liquid ammonia. Okay, so you can have liquid ammonia that boils easily, so you boil that. The vapors, just as water vapors were used, the vapors of this liquid ammonia, they would push the turbine of the generator. Okay, they pushes the turbine of the generator, and then that generator generates electricity. So this is how it is used. But then what is the role played by the colder portion? What we do is, this colder portion is pumped up, because all this is happening near the surface. So this colder portion is pumped up. Don't forget that will require some energy. Okay. So the colder water comes up, and what it does, it liquefies the vapors once again to the liquid ammonia. The vapors which were in the vapor form, of course, gaseous form, is converted into liquid ammonia. What do we achieve by this? Then it becomes a cycle. You have liquid ammonia, you are using the heat to boil it, to convert the vapors, to turn the vapors, to push the turbine, and therefore electricity is generated. But you want to have it again and again, you want to have it on a cycle basis. So you have the colder water being pumped up, which converts the vapor into liquid ammonia again, which would be vaporized once again for the second time, and third time, and fourth time, right? So this you would achieve a cycle. Again, you would see that it has a very, since there is a large amount of hot surface of sea available, so the potential is high. One can, in principle, use the large sea surface, large heated sea surface to obtain the electrical energy. That is theoretical, but the only problem is that commercially it is, but to use it in the commercial way is very difficult. As before, the machinery to set up commercial usage is low. You can again have it only near the ocean. That is one problem. You should have enough temperature difference. That's another problem. And of course, the machinery is difficult to set up all the while. I mean, you can have two conditions and you may not have the third condition, and therefore it has a limited use. Right? So these are the three kinds of sea energy that we can use. Well, we have a third source. We have the sun, we have the ocean, and we have our own beloved earth. Right? Do you have energy in the earth? Yes, I'm sure you all know this. This energy, the third kind of energy, is called geothermal energy. As the name suggests, geo has to do with the land, thermal has to do with the heat. So we utilize the heat which is inside earth. Now you all know that there have been, for ages, for centuries, there have been heat energy in the core of earth. It was there because of the geological changes for years. You have molten rocks inside the earth. Now these molten rocks are not stationary. They are of course in very deep hot regions, right? And what happens is they, from the earth crust, sometimes they try to come up during the movements, and they make something like hot spots. So the molten rocks, wherever they break the earth's surface or they are very near earth's surface, they create something like hot spots, and the heat is trapped in these regions. In addition to these rocks, we also have water underground. So when this water comes in contact with the hot spot, it turns into vapor. So hot spots, the heat of the molten rocks turns the water underneath into vapor, and this way steam, you can say, and this steam then comes out, and this steam when comes out can be converted into, I mean, this can push the turbine in and convert it into electrical energy, right? So these hot springs, you have hot springs coming out of earth's crust at some places. New Zealand has lots of it, US has lots of it, right? But obviously this is only where it is possible in such large amounts that one would take the trouble of converting it into electrical energy. And here in Mumbai, you would probably have heard of a place called Vajreshwari. Somewhere in Uttarakhand, we have a place called Sahasradhara. Sahasradhara has sulfur. So Vajreshwari is one definite place where hot springs are available. But again, it has not been commercially utilized. So even though it is a geothermal energy, it is not used very often. Okay, the source is inside the earth. As I said, that is the source.